In this slide, I list down some common practices on how we present frequency response functions, or we normally call it as Bode plots. Magnitude and phase are presented as a function of frequencies, and typically frequencies are presented in radians per second. As system will respond to a wide range of frequency, normally in most of the cases in our common practice, frequency is the horizontal axis, the frequencies, the domain is plotted on logarithmic scale. Magnitude of the G omega is presented in logarithmic scale, and the phase is presented in linear scale. One more word that I can mention about the magnitude plot. When I mentioned that the magnitude is presented in logarithmic scale, that is true, but more common practice, it is presented in decibel scale. To make both magnitude and phase axis linear, the magnitude, as I have already mentioned, is presented in logarithmic scale, but in more common, this magnitude is plotted in decibel scale. As you know, decibel basically is a logarithmic scale, but it is scaled up by 20. So decibel is 20 log the magnitude. Magnitude here again is presented again in decibel scale. This is a typical example of magnitude plot in our Bode diagram. Let me switch my cursor to a pointer here. As you can see here, the domain is, as I have already mentioned, presented in frequencies. The common practice is in radians per second, and as you can also see here, if you look at it carefully, the scale here of the frequency is presented in logarithmic scale. So as you can see, from 1 to 10 for 1 decade, the scale is the same as from 10 to 100, and also from 100 to 1000. While for the horizontal axis, as this is a magnitude plot, the vertical axis is the magnitude again, but it is presented in dB scale. While for the phase plot, the x-axis, the horizontal axis, is still the same, frequencies in logarithmic scale, but the vertical axis, the phase, just simply plotted in linear scale. This is an example of Bode plots. For this typical system, I have a transfer function Gs equal to 10s plus 3 divided by s times s squared plus s plus 2. So how I plot the frequency response functions for this system, for the system with this transfer function of Gs? The very first step, of course, I have to convert Gs to G omega. How we do that? It's pretty simple. We just simply have to substitute J omega to all of the s's in our transfer function. As you can see here, after I replace all of the s's with J omega, this is what I will get. To simplify the equation, this is what I will get. And then moving forward, in order to plot the magnitude of the Bode diagram, I have to find the magnitude, the absolute value of this G omega. That is when we want to find the magnitude plot in our first step. So I will just take the magnitude of this J omega. Of course, I have a fractional form of this J omega. How to find it? The magnitude of fractional form is equal to the magnitude of the numerator divided by the magnitude of the denominator. The magnitude of the numerator, obviously it will be equal to this one. 10 times 10 is 10, so I don't have to evaluate the magnitude. The magnitude of a real number is the real number by itself. Well, the magnitude of j omega plus 3 will be equal to the square root of the imaginary part, there is omega in here, square, plus the real part square, divided by the magnitude of the denominator. We have two parts in the denominator, j omega and this part, 2 minus omega square plus j omega. The magnitude of the denominator, then it will be equal to the magnitude of this part times the magnitude of this part. The magnitude of j omega, obviously it will be equal to omega square, while the magnitude of the full form of a complex number that contains real part and imaginary part will be equal to the square root of real part square plus imaginary part square. So this will be the magnitude of the j omega. But remember, if you want to construct the Bode plot of the magnitude, what we have to do, we have to present this magnitude in dB scale, and dB is 20 log of the value itself. So I will just evaluate the dB of this magnitude, or I just simply have to evaluate 20 logarithmic of this value, and this is what we will get at the end, the j omega, the magnitude in dB scale. After I completed the equation for the magnitude in dB scale, I still have to evaluate the phase or the angle of the j omega. The angle of j omega, if I have again a complex number in fractional form, the magnitude or the angle of this complex number will be equal to the angle of the numerator minus the angle of the denominator. And again, the denominator contains two parts, contains j omega, and this part, the angle of the denominator, then it will be equal to the angle of this plus the angle of this. So at the end, the angle of my j omega here is equal to the inverse tangent of the imaginary part divided by the real part, inverse tangent of omega over 3. Of course, I can neglect the angle of the constant here, 10, because angle of a real number is just simply equal to 0. And then minus the angle of j omega. Remember again, angle of a complex number is equal to inverse tangent the imaginary part divided by the real part, and this term doesn't have a real part, so it will be equal to inverse tangent of omega over 0. At the end, it will be equal to 90 degrees minus the angle of this term is equal to the inverse tangent of imaginary part divided by real part. So this will be the expression of the angle of my j omega. Once we have these two equations, the equation of the magnitude in dB scale and the equation of the angle, I can start to plot it. Basically, how to plot it, you just have to use any softwares in your computer. Excel might be the easiest software that you can use to plot it. So what we have to do, we have to list down all of the frequency of interest for your horizontal axis, calculate the logarithmic of the frequency, because we are going to plot the magnitude and the angle in as a function of frequency in logarithmic scale. And then the third column here is the magnitude of my GJ omega based on the equation that we have already derived in the previous slide. The next column here contains the angle of the frequency response function of the GJ omega based on the equation that we also have derived in the previous slide. After I plotted the magnitude in dB scale as a function of the logarithmic of the frequency, I will get the first plot. So as you can see here, this is the magnitude in dB scale as a function of frequency in logarithmic scale. And for the second plot, I plot the angle here, the fourth column of this table, against the frequency in logarithmic scale. So this is the plot of the phase of the Bode diagram for my GJ omega. So these are the two plots of the Bode diagram that normally we have to present for our GJ omega. One thing that I want to mention here, if you have two linear systems, two linear dynamic system, let's say you have two systems, one has a transfer function of GS, the second system, the transfer function is equal to HS. If you put these two systems in serial connection, in such the equivalent transfer function of these two systems connected in serial connection is equal to G times H. Obviously, the magnitude plot of this equivalent system will be equal to the magnitude of the GJ omega in dB scale plus the magnitude of HJ omega in dB scale. Because as you know, if you have two numbers, you multiply these two numbers. If you present it in dB scale or in logarithmic scale, it will become a summation. While for the angle of GH will be equal to the angle of G plus the angle of H. Okay, probably from this slide on forward, I will just mention G when I want to refer to GJ omega, and I will refer just simply to H when I want to mention HJ omega, just to make my the discussion easier. Okay, so in this case then what we can conclude, given both plots of GJ omega and HJ omega, we can easily get the both plots of GJ omega times HJ omega. The both plots of these two systems connected in series. Let's take this example then. Now I have a complex system GS, as you can see in this slide. Obviously from this equation we can see that this system GS has one finite zero, which is equal to -2, and I have four poles here. One single pole at the origin, one pole at -10, and a pair of complex conjugate pole from this quadratic equation, right? Now I want to sketch the both plots of this GS. This system, this GS, anyhow, I can factorize it into this four terms like this, where gs now it's equal to 1 over s times s plus 2 over 2 times 10 over s plus 10 times 20 over s squared plus 2s plus 20. So now I will assume, I will analyze both plots of these individual simpler systems after I factorize this gs into these four simpler terms. If somehow we know the both plots of these individual simpler systems, in order to find the both plots of this gs, what we have to do, we just have to sum them all. Okay, let's take a look step by step wise on how we will construct the both plots of gs. Again, as I have already mentioned, at this point I will just assume gs equal to g1s times g2s times g3s times g4s, right? I will just assume gs is constructed from four simpler systems connected in serial connection. If by any means I know the both plots of g1 is the one that has a form of 1 over s. If by any means I know the both plots of g1s, like this one, the one that you see in this slide, and again by any means I know how the plot of g2 is, as you can see in this slide, and this is the plots of g3s. The last one here, I know the plots of g4s. So I know the both plots of all of g1, g2, g3 and g4. The final step, if I want to find the both plots of gs, what I have to do, I will just simply sum the plots of g1, g2, g3, g4, both for the magnitudes and for the phase plots. Let's take a look a bit more detail for magnitude now. So if this is the first one here is the magnitude plots of the g1 of 1 over s, and this is the plot, the magnitude plot of g2s, or which is equal to s plus 2 over 2, and I plot again here the magnitude of g3 and g4 accordingly. The total of these plots will be equal to the magnitude plot of gs. That is for the magnitude. While for the phase plot, I will do the same thing. If by any means again I know this is the plot of g1 and this is the plot of g2, respectively I know the plot of g3 and g4, the total plot of these four phase plots is equal to the phase plot of the gs. So that is the concept of how we are later on going to plot a complex system. So as a summary here, both plots that contain magnitude and phase plots against the frequency in logarithmic scale will have a dB scale for the vertical axis in the magnitude plot and just simply a linear scale for the phase plot. The both plots, either for magnitude or for the phase, it will vary with the frequencies. It will vary at low frequency, at a corner frequency, and at the high frequency regions. What do I mean by corner? I will explain it a bit more detail in the next short video, but in short, what I can mention here, the corner frequency is the frequency at which the magnitude plot will change the direction of the plot significantly. We will come back to that in the next short video. Both plots of simple systems like the one that we have already mentioned before have been presented. A general transfer function basically is a combination of zeros and poles comprising a simpler transfer function of systems.